Hello friends, in this video I will be talking about Kohonen self-organizing map or KSOFM. So let us understand the training algorithm first and then we'll do a question. Step 0 is to initialize the weights. Random values may be assumed. Initialize the learning rate alpha. Step 1 is to calculate square of the Euclidean distance, that is for each j equal to 1 to m, dj equal to double sigma I equal to 1 to n represents the number of input vectors, j equal to 1 to m represents the number of clusters, xi is input, wij is the weight with which the input vector is associated with the cluster. See, for example, if we have two clusters and 4 input vectors, then we need to calculate the square of the Euclidean distance of x1 with y1 and y2. And out of these two, whichever distance is lower, that cluster will be called as the winning cluster. See, step 2, find winning unit index j so that dj is minimum. So whichever distance between the cluster is lower, is that particular cluster will be called as the winning cluster. Step 3 is to, for all units j within a specific neighborhood of j and for all I, calculate the new weights, and we'll apply weight updation on the winning cluster by the formula wij new equal to wij old plus alpha xi minus wj old. This is the architecture model for Kohonen self-organizing map, where all these x1, xi, xn, these all are the input vectors, and y1, yj, ym, all these are the clusters. So let us look at the question. Construct KSOFM to cluster 4 given vectors. We have been given 4 vectors. Number of clusters to be formed is 2. Assume an initial learning rate of 0.5. So we have been given 2 clusters, therefore we'll make 2 clusters y1 and y2, and we have been given 4 input vectors, therefore x1, x2, x3, x4, and they all are connected with the clusters. Now first step is to initialize the weights randomly between 0 and 1. So this is 0.2, 0.4, 0.6, 0.8. These all represents the weights with which x1, x2, x3, x4 are connected with the cluster y1. And 0.9, 0.7, 0.5, 0.3, these represents the weights with which x1, x2, x3, x4 are connected with the cluster unit y2. Now let us see for the first input vector, that is x equal to 0, 0, 1, 1. We need to calculate the Euclidean distance. How do we calculate the Euclidean distance? Let's see. We need to calculate the Euclidean distance between the cluster 1 and the input vector 0, 0, 1, 1. So let us see. D1 is equal to, D1 represents the Euclidean distance between the cluster 1 and the input vector x1. So we'll do it like this. 0.2, since these represents the weight with which all the input vectors are connected to cluster 1, therefore 0.2 minus 0, 0.2 minus 0 ka whole square plus 0.4 minus 0 whole square plus 0.6 minus 1 whole square plus 0.8 minus 1 whole square, will get 0.4. Similarly, we'll calculate the square of the Euclidean distance between the input vector x and the cluster unit y2. We proceed on to the similar manner. 0.9, since these weight represents the weight with which the input vector is connected to y2, therefore we'll calculate 0.9 minus 0 ka whole square plus 0.7 minus 0 whole square plus 0.5 minus 1 whole square plus 0.3 minus 1 whole square, and we'll calculate d2, that comes out to be 2.04. Now see, d1 is 0.4 and d2 is 2.04. Therefore whichever is less is called the winning cluster, so d1 will be the winning cluster. Now we'll apply weight updation on the winning cluster unit, that is j equal to 1. So wij new equal to wij old plus alpha xi minus wij, where j equal to 1. So wi1 new equal to wi1 old plus alpha xi minus wi1 old. Now let us see w11 new. Now we'll apply weight updation between, we'll apply w11 new, w21, w31, w41. So w11 new will come out to be w11 old, that is 0.2 plus 0.5, that is alpha, x1 is 0 minus w11 old is 0.2, that is 0.1. Similarly, w21 new equal to w21 old, which is 0.4 plus alpha 0.5, x2 we'll calculate, x2 is 0, so 0 minus 0.4 is 0.2. Similarly, w31 new is 0.8, w4 new is W41 new is 0.9. So after presenting the first input vector, we'll get updated weight metrics like 0.1, 0.2, 0.8, 0.9, since we have updated the weights on cluster 1, and 0.9, 0.7, 0.0, 0.5, 0.3, which will remain the same as we have not applied weight updation in cluster 2. Now let us see for the second input vector, x equal to 1, 0, 0, 0. We calculate the square of the Euclidean distance. Similarly, d1 is equal to 0.1 minus 1 whole square plus 0.2 minus 0 whole square plus 0.8 minus 0 whole square plus 0.9 minus 0 whole square. We'll get 2.3. Similarly, we'll calculate d2 0.9 minus 1 whole square, 0.7 minus 0 whole square, 0.5 minus 0.0 whole square plus 0.3 minus 0 whole square. We'll calculate 0.84. Now whichever is lower, since d2 is lower, therefore the winning cluster unit is d2. So we'll apply weight updation on the cluster 2. So Wij new equal to Wij old plus alpha xi minus Wij old. Since we apply weight updation on j equal to 2, therefore we write W12 new is equal to W12 old plus alpha x1 minus W12 old, which is 0.9 plus 0.5 into 1 minus 0.9, which will get 0.95. Similarly, we'll get W22 new as 0.35, W32 new as 0.25, W42 new as 0.15. After presenting the second input vector, we'll get updated weight metrics like 0.1, 0.2, 0.8, 0.9, 0.95, 0.35, 0.25, 0.15. For the third input vector, we'll get updated weight metrics like this, and all the values are presented here. Now for the fourth input vector, we'll get the values like this. Here the winning cluster is first winning cluster. So this is the updated weight metrics, and final architecture will be like this between y1 and y2 and x1, x2, x3, x4. So friends, if you like the video, please like, subscribe and share. Thank you.